Xingting Wang. Yes.
Yes.
So let's see if you can share your screen.
Yeah, let me try.
Yes.
Can you see my screen?
Yes.
Okay. Yeah, let me. Yeah.
That's perfect. Okay, then we'll start with our next talk, Twisting of Graded Quantum Groups and Solutions to the Quantum Yang-Baxter Equation by Xingting Wang. So whenever you like, please go ahead.
Thank you for the introduction and thank you for the invitation. I'm very happy to speak here. So let me repeat my title. So it's Twisting of Graded Quantum Groups and the Solutions of the Quantum Yang-Baxter Equation. And this is a joint work with Hongdi Huang, Nguyen, Charlotte, Kent, Vashaw and Padmini Veerapen. So let me first give some overviews of the line themes of my talk. So I'm going to divide my talks into 4 parts. First, I'm talking about the twistings of quantum groups. Basically, I'm going to introduce 2 different versions of that. And in the second part, I'm going to answer when one part equal to the other. So one is called the Zhang twist, the other is called Twocode cycle twist. I'm going to talk about the applications in Manin's universal quantum groups. And the last part, I'm going to find some applications of the twisting I'm defined before, especially to the solutions of quantum Yang-Baxter equations. So let me first start with some basics notations. I'm going to use K overall to denote a base field. So I don't need the characteristic to be positive or 0. Most time, arbitrary characteristic will work. And I'm going to work with a bialgebra. So I'm going to use the standard notations B for bialgebra with structure maps, the multiplication denoted by M, the unit map U with the coalgebra structure given by delta and epsilon. And additionally, if a bialgebra has an antipode, we say it's a Hopf algebra. And most of the time, people like to say Hopf algebra of quantum groups. So in my dictionary, they are the same. So Hopf algebra is a quantum group. And in specifically, I like to use this curly H to mean the Hopf envelope of arbitrary bialgebra. So what is that? So if you give me a bialgebra, usually it will not possess an antipode. So I can construct the smallest Hopf algebra containing B, and that is called Hopf envelope of B. So it's the smallest Hopf algebra you can build up from a bialgebra. And I use curly H to denote that. And let me first talk about some history about twistings, especially twistings for quantum groups. So the first thing is motivated by the tensor equivalence between modular categories. So in 1987, Dreamfield introduced the notion called Dreamfield twist. So Dreamfield twist J is actually an element inside the tensor product of H with self. Now, using the so-called Dreamfield element, Dreamfield twist J, we can deform the original Hopf algebra. And the deformed one is denoted by H up J, H up J. So how the deformation works, right? So as algebra, you keep the same algebra. So Hj is same as H as an algebra. But the J will play a role in the new co-multiplication. So to be more precise, actually, the co-multiplication delta is get conjugated by J. And by some properties on J, you can prove that this new one is still a Hopf algebra. So this is called the Dreamfield twist of H. And also, as I already mentioned before, it has a categorical background. Is you can show that if you gave me 2 finite dimensional Hopf algebra, H and K, you consider their representation categories, finite dimensional modules. And the 2 finite dimensional module categories are tensor equivalent if only if one is a Dreamfield twist of the other. So this Dreamfield twist completely classify all the tensor category of module categories. Tensor structures are module category of a finite dimensional Hopf algebra. Now, due to that Dreamfield twist, in later years, 1993 to be precise, Doi and Takeuchi introduced a dual version of Dreamfield twist. And that is the main character of my talk today, is called Twocode cycle twist. Okay, so the way is you just do the opposite way. And remember, the Dreamfield twist keeps the algebra structure while deform the coalgebra structure. So at this time, the Twocode cycle twist just do the opposite way. So it keep as a coalgebra, but at the same time, the algebra structure of the original Hopf algebra get deformed by this Twocode cycle sigma. So let me just be a little bit technical. So I'm going to introduce what is a Twocode cycle. Okay, so remember the Dreamfield twist is an element inside H tensor H. So in the dual version, the Twocode cycle should be something from H tensor H to K. And more precisely, you want it to be invertible convolution invertible, okay? And satisfy the properties over there. And it's very easy. So if H is just a group algebra, we know quantum groups can be considered as non-commutative groups, right? So if H degenerates of a group algebra, this Twocode cycle, just by its name, is a Twocode cycle on the group in the bar construction. So it's just can be considered as a generalization of a Twocode cycle in the group case. And also they are formally due to each other by the following description. If you take J inside H tensor H, then the dual of J is actually a Twocode cycle. So it's in finite dimensional case, everything is due to each other. Dreamfield twist, Twocode cycle twist are due to each other by vector space due. Okay, so that's one of the players of twistings we are going to consider today, is how to twist a Hopf algebra by a Twocode cycle. Now, let me introduce another twisting, which have a totally different background, is from a so-called a non-commutative projective algebraic geometry. So this topic is actually introduced by Artin and Tate by classifying some non-commutative graded algebras of global dimension 3. And later in 1996, Zhang introduced another notion of twistings, but this time not for Hopf algebras, but for families of graded algebras. So let me be more precise. So take a graded algebra. So here graded algebra is the same thing. We talk about commutative graded algebra. So you have Z grading. You can actually grade by arbitrary abelian groups, but for the sake of this talk, I'm just going to let A to be graded by integer Z. And also I take a graded automorphism of A. So it's an algebra automorphism where I'll keep track of the gradings. Now we can define two-sided twist. So let me keep notion consistent. So a right Zhang twist, we denote by A up phi is defined as follows. So I keep the grading as the same. So A phi is same as A with the grading as a graded vector space. But the structures, the graded multiplication get twisted. So what's the twisting will work, right? So in this time, I take two homogeneous elements Rs in A. When you multiply them, you're not going to multiply them as usual in A, but when you multiply two together, the second component will get twisted by the R times of the automorphism. The R times R is denoted by the order or the degree of the first element. So you see, if you put everything in degree Z, you have no twisting. But if you have positive or negative degrees, the multiplication changes, right? When you multiply 2 degree 1 element, certainly it changes. Now, but interesting thing that is not defined arbitrarily just for a new algebra. It also have a categorical motivation. It is further proved that if you take the original graded algebra and take the Zhang twist of that, if you consider the graded modules, they are actually equivalent. And the graded modules in the connected commutative can consider to recover the quasi-coherent shape. So it's like it has a motivation in the project algebraic geometry. Okay, now I have finished, I think, the main two characters of my talk, the Twocode cycle and the Zhang twist. And the next part of my talk, I'm going to try to link them together. So it'll be a very specific question I want to answer, and it's already in the title, right? How can Zhang twist actually be a two-co-cycle twist. So let me be more precise. We know we can deform the algebra structures by the following previous descriptions, two-co-cycle or Zhang twist. But we know both twisting need some conditions on A, right? For example, two-co-cycle need A to be a Hopf algebra, while Zhang twist need algebra to be Z-graded, at least. So we like to answer the following question. So suppose I gave me a Hopf algebra. Now I can do two-co-cycle twist. At the same time, it has a Z grading. We'll see some examples that quantum groups do have natural Z gradings. So it's not something very strict. A lot of examples have Z gradings. Now we want to ask the following question. When a Zhang twist can be realized or can be a two-co-cycle twist? Okay, and we're going to answer this question in two aspects. First is, so first thing maybe everybody like to ask is, we don't know if Zhang twist of H is still a Hopf algebra, right? Because Zhang twist does not care anything about the co-algebra structure. So it's not a guarantee that arbitrary Zhang twist of Z-graded Hopf algebra will naturally still have a Hopf structure. So the first question is like, we need to answer first is when a Zhang twist of a Hopf algebra still possess a Hopf structure. And after that condition, we can ask whether this new Hopf algebra can be realized by a two-co-cycle. If so, how can we write the two-co-cycle twist explicitly down? And that is the main concern of our talk. And we'll see some partial answers right away after this. So in order to answer the first question, I need some conditions on the Hopf algebra, right? Not every Z-graded Hopf algebra will have survived under the Zhang twist. So the condition we get or we define is so-called twisting conditions, okay? And this condition can be defined for bialgebra. So you don't need a Hopf algebra, actually. It can be a little bit loosen the condition to be only for bialgebra. So what is a twisting condition? Only T1, T2. So T1 is certainly should be there because I want it to be Z-graded. And also I don't care about the co-algebra structure. So it's only Z-graded algebra, no Z-graded co-algebra. And the second one completely says it's not graded as a Hopf algebra, okay? The second one means that if you apply the co-multiplication on each homogeneous piece, you have a diagonal map. So the condition 2 means delta is a diagonal map of the grading. And for this condition T2, we know that the bialgebra is not Z-graded as a bialgebra because the T2 condition fails to keep the grading. It's just a diagonal map. Okay, so before I say some result which says that the twisting condition actually works for Zhang twist to make a Hopf algebra again, maybe we should look at some very, very, very basic examples to support our definition. So let me look at a very easy example. So I take a positive integer n, which is greater than 2, equal to 2, and I consider the classical coordinate rings of the matrix algebra. Okay, so it is not quantized anymore. It's just a commutative bialgebra, which is n square polynomial rings with each variable has double indexes. Ij means the ij entries of the matrix. And we can make it into a bialgebra where we let delta xij have the following form. Usually call it so-called the co-matrix structure, co-matrix algebra, and the co-unit just make xij into delta ij. Right? It's a very standard setup. And after this, we see that is a bialgebra. But if we put a canonical ratings on that, which everybody probably will do the same, we let the algebra generate degree 1. Then, because the co-matrix algebra have this form, right? Xij equals sum, xik times xkj. So it's very easy to see that this bialgebra satisfies the twisting conditions. Okay, satisfy twisting conditions. Okay, the next example is a little bit complicated because it has some using some pre-regular forms, but it appears a lot, especially when you talk about Manin's quantum groups later is certain like the one concrete example of what kind of Manin's quantum group look like, which we'll talk about later about them. So here I take a vector space with n-dimensional. I fix spaces V1 to Vn, and I want to take a pre-regular form. So what is a pre-regular form? Everybody knows it's a bilinear form, right? V tensor V to K. So a pre-regular form is a multilinear form which satisfies some conditions. So it's a linear map from V to the m's folder tensor to K, where m is greater or equal to 2. M is 2 is a non-degenerate bilinear form. But m greater or equal to 2, we need some conditions on the multilinear form. So here the condition is a cyclic condition. So I can find a linear map phi, which is endomorphism on the vector space V. Here I just say a matrix GLNK, such that when you permute or cyclic permute the m variables on the m folders n, you move the last one to the first one, right? You're going to have a twisting, and the twisting is given by this map phi. So if phi's identity is like cyclic permutations. But just like the bilinear form, you see that when you twist the two ones, you're going to have a difference. And this difference is captured by this map phi. So this is how you define so-called pre-regular forms. And for simplicity, I'm going to write the evaluation of pre-regular form on VI1, VIM just by recording the indices of these fixed spaces to make sure. Then for any pre-regular form, we can construct a Hopf algebra. And the Hopf algebra play a lot of same thing as the quantum Manin's quantum group later, but we just see the construction very explicitly. So I have n squared plus 2 generators, Aij, Bij, and so-called quantum determinant D plus minus 1, satisfy the following relations. So I'm not going to explain why these relations work out, but they have deep reasons why we need these relations, okay? A consequence of that, if you make everything use of the definition pre-regular form, you can check that it's actually a Hopf algebra. It's a Hopf algebra, but we do need to use the pre-regular form, especially the cyclic condition, which the matrix play a role inside. But it is also a satisfy the twisting condition. So even though the relation looks a little bit complicated, but if you make Aij into degree 1, Bij into degree minus 1, where the determinant D has degree m is m folder, m linear form m, then you can check the same thing that it satisfies the twisting conditions. So it's another example which the twisting conditions appear very natural. Okay. So now let me state one result as partial answers on my first question. So when is a Zhang twist give you again a Hopf algebra? I want to do it first in the bialgebra case. So if you have a bialgebra has the twisting condition, then for every graded bialgebra automorphism phi, you can do the twisting B phi, because B is Z graded, right? So you can do B phi. And as long as the twisting condition works, the B phi is again a bialgebra. And it's pretty simple to check the answer because we don't change the coalgebra structure. You can literally check by using the twisting condition. The coalgebra structure exists and also it's compatible with the new multiplication, so it's still a bialgebra. And in the special case, if it is a Hopf algebra, means we have an additional antipode, then you can define a twisted antipode, which here I use the formula S phi. They just have a twisting by the automorphism by a certain degree for every homogeneous, then it's again, there will be a Hopf algebra. Okay, so that's the first answer. We see it, as long as the bialgebra Hopf algebra has a twisting condition, then the Zhang twist will still give you a bio Hopf respectively algebra. Then we jump to the second question. The second question is when that Zhang twist is actually a 2 co-cycle twist, right? So in order to give partial answers to that question, we're going to give another new definition, which is called a twisting pair. So what is a twisting pair? It's very like the conjugation in the group case. We'll see that it's actually generalized that. But let me give you an abstract definition first. Then as the previous one, I'm going to walk through examples to let you digest concrete understanding what twisting pair would be look like in the specific example. So twist pair is a pair of algebra automorphisms. So we don't need bialgebra, just algebra automorphisms. And also we don't need to keep the gradients, anything, no need, just two algebra automorphisms set by the following two conditions. So the second condition, it just means it's well behaved with a co-multiplication. The first one, you can say that in this easy way, just if you think phi 1, phi 2 as maps from B to B, they are left or right co-module maps. Because if you have a bialgebra, it's a co-module of itself, right? So phi 1, phi 2 are just left and right co-module maps. And that's probably easy way to remember. Okay, so before I give you an example, maybe I should point one thing is is that the twisting pairs play well with the Hopf envelope. We say the Hopf envelope a while ago, right? Maybe in the basic setup, we say that if you have me a bialgebra, I can construct a Hopf algebra, which is the smallest one you can get by inverting things by the antipode, right? So actually the twisting pairs behave well with Hopf envelope. We can show that there's a 1-to-1 correspondence between twisting pairs of B and twisting pairs of its Hopf envelope. So you may ask this question, why we care of Hopf envelopes? Because if you, for a specific example, if you have Hopf algebra, usually it's hard to compute its Hopf envelope because the antipode, right? Many things will get inverted like the group-like elements, right? So you get a lot of invertible elements, which makes the calculation harder. But if you look at the bialgebra, usually some of the relations are very easy. So for the sake of calculation, this proposition makes computing twisting pairs an easy work. That's why we want this. And also there's another way to describe twisting pair, which I don't think we need to know. So I just list there because I'm going to skip that. It's not quite difficult. It's just by representation mean of few twisting pairs is actually linked to those one-dimensional representations. But that's something we don't need to talk too much today. So let me go directly to the examples. So I'm pick some examples which the twisting pair become a little bit more canonical. For example, I take a group, algebraic groups, right? I consider its coordinate rings. We know it's a commutative Hopf algebra, and that's how the Hopf algebra get involved. And if we take a map, right? The algebra map from the coordinate ring to K, and we know such map is given by maximum ideals of the coordinate ring, which actually give me exactly elements in the group. Now, by the previous technical lemma, which we don't need to be too much get involved, but associated to this algebra map, you can get two translations on the group, and at the same time will be translations on the coordinate rings by taking the regular functions. So one is RG, the other LG. You just play rules like right multiplication on G and the left multiplication on G, right? So you can show just by following the definition that all the twisting pairs on the coordinate rings of G is given by such translations. Basically, right multiplied by G, followed by left multiplied by G inverse, which is a conjugation, right? So it just, as I already said, that twisting pair is just a way to generalize conjugation of groups to quantum groups in some sense. Okay, so the next example is a little bit complicated. Maybe I should not involve, but maybe if I put there, just say you can compute it. It looks like complicated, but actually for many concrete examples of Hopf algebras, you can do it just by a little bit manipulating of the definition. So here the Hopf algebra pick is so-called co-solving Hopf algebras. It's given by a matrix F, and the relations is given by two sets of generators, and the relation involving this capital F. And this is introduced actually by Vashaw in his paper co-solving Hopf algebras. The good thing for co-solving Hopf algebra is actually the co-representation has a pivotal structure, which you can use to define quantum traces. So that's another thing. So in this special case, you can compute all possible twisting pairs. So I just say the reason phi 1, phi 2 have two generators UV, and the phi 1, phi 2 are actually given by a single matrix A that commutes with the transpose of F. So in this example, you can determine all the possible twisting pairs, just like the coordinate ring case. Okay, now let me give you another result. So the answer is this, that if you give me a twisting pair, two graded automorphisms, phi 1, phi 2, then I can define a two co-cycle on H. So that's the main thing we introduced twisting pairs, is you can define a two co-cycle sigma associated with phi 1, phi 2. Now you may ask why we need the phi 1, phi 2, right? Because in the definition of two co-cycle twist, we require this two co-cycle twist to have a convolution inverse, right? So phi 2 play in role of sigma, and the phi 1 actually defines convolution inverse. Okay, and the formula is pretty much very explicit, right? You give me xy, you just apply epsilon. But when you have y, you have a twisting by phi 2 to the degree of x. For sure, it works for any two homogeneous of H. So, which means that I do need a twisting conditions on H as a assumption. Then we can show that if you use the two co-cycle twist I defined by using twisting pair, that the two co-cycle twist H sigma is exactly given by the Zhang twist, where the automorphism is a composition of phi 1, phi 2, which you can think about the conjugation, right? So you take phi 1, phi 2 twist H is same as giving you a two co-cycle twist by the two co-cycle explicitly given as in the condition 1. And one thing I think that might be a good application is most of the time, except H is a group algebra. If H is a group algebra, two co-cycle twist is exact given by two co-cycles in the Hochschild two co-cycles, right? But for general Hopf algebra, it usually is very hard to determine, especially write explicitly for all those two co-cycles. So using twisting pairs, it's become a little bit easy because you see the expression of sigma is very, very much explicit as long as you know phi 1, phi 2. So I think that is also one of the main applications. By instead of looking all the possible two co-cycles, you can pin down to those given by twisting pair. And that's one of the ideas later in the application of Yang-Baxter equation solutions. I will see that argument make perfect sense over there. Okay, so quickly let me do the third part, Manin's quantum groups. We see that some examples of Manin's are associated before, right, using multilinear forms. But let me give you a general definition. It's actually defined by universal properties. So let me go through. So I take a so-called quadratic algebra. So A is a quadratic algebra. So it's generally in degree 1 with quadratic relations. And in no sense, in no requirement, we need is commutative. Everything is non-commutative. But we need relations to in degree 2, just like the polynomial rings, which is the example of quadratic algebra. Then we need a finite generator, which is usually we need to add a finite generation there. Then we can define so-called universal bialgebra. So, and it's given by Manin in his, I think it's 1988 lecture notes on non-commutative algebraic geometries, where he trying to define these, now that we call the symmetric groups of non-commutative algebras. So if you have a polynomial ring, you have the classical symmetric groups, right? The general linear groups, subgroups of that. But for non-commutative algebra, you only look at the group actions is not a good way, because generally speaking, non-commutative algebra possess less classical symmetries. So what's the usual way to find these hidden, we call quantum symmetries of non-classical objects, is to using this kind of definition. And that's one of the favor of that is using universal properties. So I consider all the possible coactions on A. So what is a coaction? Maybe I should quickly say that. It's just comodules. So you have a comodules over B, where the comodule structure respect to the multiplication A. That's usually we say that the bialgebra coax on A. So you look at all the possible coactions on A by algebras, while at the same time it preserves the grading. So the grading really plays rules here. That's why I need a quadratic algebra. And the Manin's universal bialgebra is the biggest one that you allowed to coax on A. What does that mean? It means that the universal bialgebra has a coaction on A, which means that you have a comodule map from A to the bialgebra tensor A. Here, and LA just means the left side universal bialgebra. As I said, the coaction means comodule, and the multiplication also be respected by the comodule structure. And it's the biggest one, means that if you have any other B bialgebra coax that, then there is a unique bialgebra map fact through this universal one. Now this defines so-called universal bialgebra. If you require all the coaction by Hopf algebras, you get Manin's quantum groups. Manin's quantum, which we use alter LA. I said that we consider as so-called the biggest non-symmetric, non-classical symmetrical quantum symmetric groups of A. So what are they, right? So one thing we have to be very faced with courage is that these are gigantic things, which means that totally non-commutative, and the representation is bad. Not finite GK. I don't think it's finite global dimension. Not very good things. So let's look at one of them, right? So I take the easiest one, except the polynomial in 1 degree. In general degree Kx, then it's easy. It's just the group algebra on the cyclic group. But as long as we jump to a polynomial of 2 variables, I can get a representation of alter A, which generate by 4 elements A, B, C, D with an inverse of this delta AD minus BC with these relations. And it's totally highly non-commutative and not finite Gelfand-Kirchhoff dimension for sure. But the great thing that we can make it into a Hopf algebra by letting M have this matrix coalgebra. We see that before. And also the antipode is given by using the invert of this element delta. And sometimes this delta is called the quantum determinant. Okay, so the things we do is, even though the algebra structures are pretty crazy, but actually we can compute all the twisting pairs. And the one thing we show is that if you only consider these twisting pairs, that on the Manin's quantum groups, they're actually given by the graded algebra automorphism of A. So it means that there are not a lot of choices at most GLN. Okay, so one thing we show that is if you give me a automorphism of A graded, we can lift up to a universal quantum group of A. And the reverse is set, everything given that. And as a consequence, we show that the co-representations of this will only depend on the graded module category of A. Graded module category means that I suggest that actually that thing should be defined for categorically rather than using number. Even though I don't do that, but I think this result suggests there should be a categorical approach to what quantum symmetry is, which I don't know, but this is actually a consequence of that. Okay, so I have last part. I think I have probably 10 minutes to 15 minutes, so I should be able to finish the last part. Let me see why I cannot. Oh, okay. So now I'm going to give you one example of twisting pairs for given solutions of quantum Yang-Baxter equations. So let me first give you a quick review, I think, before I say the application. So what is quantum Yang-Baxter equation, right? It's same equivalent to braided solutions. If you try to braid two strings, you have two ways to braid three strings, right? And the equivalent, if there's two different braiding, is called a braid equation. And the quantum Yang-Baxter is almost the same, except flipping probably. So I take a finite dimensional vector space. I consider possible linear transformation or endomorphisms of two tensors of V. Being considered, R can be considered as a flipping, right? V tensor V to V tensor V. Then R is called a solution of the QYBE. If in the three tensors of V, we have these equations. So how to read this equation? That first thing is we have the upscript, right? Like 1, 3. It just means that you let this operate acting on first and the third components of the three tensors. Keep the middle one identity. So it means that I first act on 2, 3, 1, 3, 1, 2 is same as first act on 1, 2, 1, 3, 2, 3. And that is same as if you write diagonal or graphically, or maybe I should write the diagonal equation in diagraphic manner. Maybe that's easy to understand. So but whenever you have such R satisfy the equations, is called one solution of the quantum Yang-Baxter. So now let me quickly explain the ideas, how to use twisting pairs to give new solutions based on the ones probably we know. Is I take V and fix the basis. We know V is dimension n, so the R matrix, R is usually called R matrix, as I said before, is actually given by n squared times n squared matrices. And I need to use up lower matrix. Each of them have a double index to denote a R matrix in the following way. See how it acts on the pure tensor XK, XL. And if I give me R matrix, there's a very classical construction in quantum group. It's called the FRT construction. So I'm quickly review it. Is you start from an R matrix, you can get a quasi-triangular bialgebra. So I use the notion AR, and the quasi-triangular structure is given by theta. So maybe I need to say a little bit about details, but it's not that important in the whole ideas. The basic idea is you give me R solution, I can give a algebra. It's actually a quadratic algebra with n squared generators with quadratic relations. And these relations are actually given by the matrix R. And it's a bialgebra, so it has a co-algebra structure just by define co-matrix algebra structure on these n squared generators. And most importantly, this bialgebra has a co-quasi-triangular structure. So what is a co-quasi-triangular? It's also a map from AR tensor alpha, but it's not two co-cycles, which I said before. It's totally different. So this co-triangular structure just means that if you take the co-module categories, the co-representation is a braided category. You have a braided structure, means you can braid two co-modules, which using this structure. And this is called co-quasi-triangular structure. Okay, so also we sometimes, not every time, but sometimes AI is a bialgebra, right? It's no sense, it's a Hopf algebra. But in most of the examples we care about is that you can find a central group-like element inside this FRT constructor. And when you invert it, it will become the Hopf algebra. In most of the examples we care about, you get a Hopf algebra, and that is actually the Hopf envelope. Okay, and that's very important point. The Hopf envelope of AR can be obtained by inverting some central group-like element. Okay, and the things here is the original AR, if you take the co-module categories, and it's a braided category, right? So, And I can use the idea of equivalence about Twocode cycles. If you find a Twocode cycle on sigma, sigma on AR, then I can have an equivalent comodule category. I consider Twocode cycle twist of AR. And the interesting thing is that since the left side, we say it's a braided category, right? A co-quasi-triangular structure. So if you have a Twocode cycle of AR, the quasi-triangular structure can be naturally passed to the right side by the following formula. By the formula. And I said the braided equations is almost the same as quantum Yang-Baxter equations, right? So being a braided category or having a braided structure is almost same. Say you have a solution of the quantum Yang-Baxter equations. So the idea is that the original quantum Yang-Baxter solution lives in the left side of the module categories. And if you can twist it by a Twocode cycle twist, you get a new solution on the right side by using the new quasi-triangular structure, which I stated in the red color side in the box. That's the philosophy, how you get new solutions by looking at equivalence of braided categories. But theoretically it works, but practically speaking, as I said, computing Twocode cycles of AR is not an easy thing. Even though we know AR is a quadratic algebra, but after inverting G, and you don't have a good PPW basis, and you don't know how much element you should compute, right? So basically speaking, finding all possible Twocode cycles on AR, at least to me, it seemed like very hard to do, okay? But I said we have a very special Twocode cycle twist, which is given by twisting pairs. So next thing, this is just given by the new solution, which I said before, right? Using the equivalence categories, the solutions are pushed forward to the new category by the formula here. But if we consider the twisting pairs, actually it's not very hard to do. So actually we can compute all the possible twisting pairs on AR, which give you specific Twocode cycle twist. And we can do it very explicitly, is that these twisting pairs actually given by two matrices, alpha, beta, which satisfy this quadratic relations. So it is completely a doable thing because there are not many quadratic relations. You can use computers or by hand sometimes to complete all the possible matrix there. And that by combining the general formula we get, you get a new solutions in terms of the twisting pair. So this is one strategy we can use by applying twisting pair. And I'm giving you a very, very easy example. So I'm taking the classical Yang-Baxter operators RQ, depending on parameter Q. So it's just have three different cases, I equal to J, I less J, I greater J. Okay, that's called the classical Yang-Baxter operator. And I want to twist it by twisting pairs. So what we do is first figure out what is FRT construction of that. And it's well known in the literature. So it's actually the so-called quantized coordinate rings of n by n matrices. So, and that's a general, it's just a quantized version of the matrix algebra we did before. Remember when Q is 1, that's one we did before. Here we have a parameter Q, so we quantize the algebra relation a little bit, where the bialgebra structure remains the same. Now, some facts is that the FRT construction of the quantum Yang-Baxter equation, the RQ is the same as the matrix quantized matrix algebras. And you do have a central element after localization, you get a Hopf algebra. That's called a quantized corner ring of general linear group. And you can compute all the twisting pairs there. Just by the formula I did before, is actually given by one invertible matrix, alpha ij, okay, alpha ij. And depending on the Q, you have three scenarios. If Q is 1, you get the commutative case, then you can take any arbitrary alpha ij. When characteristic not 2, Q is -1, you have a generalized permutation matrix. But if Q is not 1 minus 1, the matrix has to be diagonal, meaning that it's almost no non-trivial twisting other than scaling the variables in a very, very mild way. So last page. So now we can do the twisting. So I write RQ as n squared times n squared formula using the canonical delta, 3 cases. And I can throw in the alpha ij, which I already know before. Then we have 3 scenarios for the new solution, Q1, Q -1. For sure, carry is not 2 here. And also Q is not minus or plus 1. Then we get the new solutions in terms of the matrix alpha, Okay? So I think that's all for my talk. Thank you very much for your attention.
Okay, thank you very much for this interesting talk, very interesting. And okay, are there any questions or comments? Let's see. Yes, Professor Militaru.
Yes, thank you. Related to the last theorem, what is the connection between these two classes of the solution of the quantum Yang-Baxter equation? So you construct one, and then another one is arising from a twisting pair, but the category of comodules are equivalent, isn't it?
Yeah. Yes.
And the solution are also equivalent, because you can classify solution of the quantum Yang-Baxter equation, you know?
Yes. First, thank you for your question. So,
the solutions are equivalent?
I'm not sure. What do you mean by 2 solutions are equivalent? Are they conjugate to matrices?
Yes, they can make. That is they can be defined when by the classifying.
Yeah, that's a good question. Actually, so I thought about this before. I don't think they are equivalent, but I don't have a nice way to explain it.
The category of comodules are equivalent.
Yeah, category of comodules are equivalent, yes.
And maybe from this equivalence of category of comodules, you can obtain that the solutions that actually are equivalent with the original one.
Okay, yeah, I will think about that. So yeah, maybe that they are equivalent. Yeah,
I'm not sure. I guess so. I feel so.
Yeah, because the equivalence of quantum Yang-Baxter equations are not defined in a category way, right? That basically defined.
Yeah.
So I'm not sure. So if equivalent of categories do induce equivalent of solution, then
no, not easy. Yeah. Not immediately. Yeah.
Yeah. But it's a good question. I would definitely like to think about more. Yeah. Thank you. Yeah.
Thank you. Nice talk.
Okay. Any other question? Well, if not, let's thank the speaker again for the very interesting talk. And